Hello, this is the presentation of our ECCV 2022 paper titled Multiscale and Cross-Scale Contrastive Learning for Semantic Segmentation. This is a joint work with Claudio Ravasio, Linton da Cruz, and Christos Bergeles from University College London, King's College London, and Moorfields Eye Hospital. Semantic segmentation can be described as a mapping from pixels to class labels. This mapping is typically approximated by a CNN, a transformer, or a hybrid model. When pixel-wise labeled examples are available, we can learn the parameters of the model by first computing a pixel-wise loss, and then using backpropagation and gradient descent to update the parameters. In this work, we seek to augment this paradigm using supervised contrastive learning for semantic segmentation. Specifically, alongside the standard pixel-wise losses, we explore the use of contrastive learning within the model's latent space Z. Using the labels, we can assign extracted feature vectors to classes and then apply a supervised contrastive loss term to impose class-aware clustering in the latent space. To this end, the popular loss function termed the info and CE loss is used. It operates on two positive embeddings, Zi and Zj, and a set of negative embeddings. As shown by Kozla et al., it can be expanded to consider a set of anchors A, each comprising a set of positives P and negatives N. Minimizing this loss maximizes a lower bound of the mutual information between positives, and thus can be used to push them close together in feature space. Several other works have also explored the application of supervised contrastive learning for semantic segmentation. Contrary to those works, we explore multi-scale and cross-scale version of contrastive learning for this task. Secondly, we do not use a memory bank as the source of more samples. We instead look within the network's multi-scale feature spaces for those samples. And thus we do not have to tune heuristics regarding the memory bank or anchor sampling. Finally, our results extend to both CNNs and transformers. The proposed method is as follows. First, given a batch of images, we obtain their multi-scale representation using the model. Then each scale's features are independently projected to a common feature space. There we perform balanced anchor sampling at each scale independently to avoid computing loss terms dominated by the majority classes. Then, for each element in the anchor set, we find positives and negatives from the anchor set itself, but also from anchor sets of other scales. Then we compute contrastive loss term at multiple scales and also across them. To motivate the use of cross-scale contrastive loss, we can think of the following example. Suppose the network sees this object and produces a global feature Zi. Then, at a higher scale, it can also produce local features Zj, each encoding a part of the object. The proposed cross-scale loss links global and local features from a single instance, but also across instances. Intuitively, this corresponds to learning to encode global object structure in a way that is predictive of local class structure and vice versa. Next, we show an ablation study of the different elements of our loss with HRNet on cityscapes. We report the mean and the standard deviation across 4 runs with different seeds. Firstly, applying a single contrastive loss term improves performance, then extending it to multiple scales boosts performance even further. And finally, the introduction of cross-scale pairs also has a positive effect on performance. We also draw similar conclusions on AD20K using a swing transformer model. Next, we compare the feature spaces learned by a model trained with cross-entropy, shown in the first row, to those learned by adding our complete loss, shown below. Color indicates class, and the model used is HRNet on cityscapes. The TSNE mappings of the features are presented in decreasing output stride order from global to more local features. We observe that only when applying our loss, feature spaces demonstrate clearly visible class-wise clusters. Moving to results, we first evaluate this approach on AD20K. On this dataset, we outperform strong CNN-based lines by considerable margins, and we are also able to improve the swing transformer for increasing model sizes. Next, on cityscapes, we also outperform various CNN-based lines and transformer-based lines. Finally, on CADIs, we compare against the state-of-the-art approach, and our loss, while achieving a modest improvement on overall MIU, is able to boost rare class MIU considerably. Finally, we show some qualitative comparisons between the baseline and our models on 8020K first, and then on the surgical scene understanding dataset. To conclude, we have presented a flexible loss applicable to various model architectures. We also showcased improvements on various datasets and models. Namely, we have obtained maximal gains on the challenging 8020K that consists of 150 semantic concepts, where the classification component of segmentation is aided by the class-aware clustered feature spaces provided by our method. Thank you for your attention, and please visit our poster.